Welcome back to our online Calc 3 class. I also wanted to say that anytime you see a question posed like this, a thing I would recommend you do is try and solve it on your own before. So you can always just pause the video, and I will try and make sure I don't just jump into these problems, but you're always going to get way more out of everything in math if you try something first. Even if you just have a little bit of an idea, maybe just to get started, I guarantee you're going to have a way better understanding if you don't just sit there and listen, if you actually try to kind of do these with me while I go over them. So today the plan is to basically make sure that we understand how to work with a very important operation with vectors called the dot product. And the goal was that you watched the video that I posted online regarding just the basics of vectors before that. And so we could use that to do a problem like this. And then we will talk about the dot product here in a little bit. So to do something like this, I would personally start by drawing what it's basically saying. So we have a vector that lies in the first quadrant. So we got quadrants, so we're in 2D. And it makes an angle of pi over 3 with the x-axis. So I'm going to say pi over 3 is something like that. That is pi over 3. And with the positive x-axis, so I know it's over there. And we also know that the magnitude of this vector is 4. So that means that this length is 4. And the goal is just find this vector in component form, and that means that we really just need to find the height of this vector over here. So what is the y component? And then we need to figure out the x component right there. And basically, you can just do this with trig, right? So if you wanted to get the, say, x coordinate there, right, we would just do cosine. So we could take the cosine of pi over 3, and we know that would be x over 4. And so 4 times the cosine of pi over 3 is the x part. And I am going to use a calculator really quick. Actually, sorry, no I'm not, because that is a nice angle, and I should definitely just know that one. Cosine of pi over 3 is 1/2, right? So 4 times 1/2 is just 2. And so we have our x component. And to do the y component, I think, we could just use sine. I mean, we could technically use tangent now, or something like that, but I'm just going to use sine. So sine of pi over 3 is going to be y over 4. And so 4 times sine of pi over 3 is equal to y. So sine of pi over 3 would be root 3 over 2. So this is just 4 times root 3 over 2, or just 2 root 3. And then we have our vector, right? Because the vector v, the vector v is just going to be given by 2 in the x component and 2 root 3 in the y. And you can write it up and down like that, or you could write it 2 and then 2 root 3 like that. It's also pretty standard to do these kind of triangular brackets and do 2 and then 2 root 3 like that. And that's basically it for that one. So I want to take some time and talk about some special kind of vectors that we're going to see a lot. So this is not necessarily a complete list, but it's definitely the big ones that I want you to know right now. So there is something called the zero vector. And whenever we write vectors, I will try and be good about this. I'm sure I'll mess up sometimes, but we try and write these in bold. So the zero vector is literally what it sounds like. It's basically just a vector where you have 0, 0, and actually I need a little more room here. And then however many entries you want, just of zeros. So it can be a 2-dimensional vector, a 3-dimensional, 4-dimensional, 5-dimensional, whatever you want, but it's just a bunch of zeros. Another really important vector is actually just called I, and actually sometimes we'll also call it I hat. We also have a J hat and a K hat. Actually, we could do U hat. N, I'll talk about in a little bit, is not necessarily going to get a hat, but the other ones might see hats a lot of times. But these four are what we call unit vectors, and I hat is, I'm going to do these like they're in 3D. So it would be the vector 1 and then 2 zeros. So it's basically just a vector that points in the x direction in just one unit over in the x there, and then nothing y and nothing in z. And j hat would be 0 and then 1 and then 0, so just 1 in the y. And k hat would be 0, 0, 1. And so k would only exist in R3, but you could have j, for example, in R2, and it would just be like 0, 1, just like that. So I shouldn't put an equal sign there, because those are not equal. So this would be in R2, and squeeze this in. This would be in R3. And so if I kind of drew those in a picture, we would have something like this, where again we got x, we got y, we got z, and we are going to go like 1, 1, 1, and we would have, oops, I wanted to switch colors, there we go. We would have something like I hat right there. We would have something like J hat right there. And then above blue, this would be K hat. And these other two down here, the U stands for a unit vector. And it's really just any vector. So U is basically a unit vector, which is really just a fancy way to say a vector of length 1. That's all it is. So I hat, J hat, K hat are actually all unit vectors, but you can have infinitely many unit vectors, tons of different directions. So there'll be lots of those. And then N is what we call a normal vector, which we won't talk about too much today, but it is an important one. And to be normal to something just means you're perpendicular. So if I it's almost easier to define this with like a picture. Say I had a sphere, and I could have a vector that just points perpendicular, like away from the sphere. So this is like 90 degrees right there. And I could have a whole bunch of them, right? I could have another one that like comes out here, and it's also 90 degrees. This shows up a lot in like physics, and forces are a lot of times perpendicular to the surface or something like that. And this is something we will definitely be working with a lot this year. A lot of Calc 3 falls into physics, basically. So sometimes you get weird statements like this, and you kind of have to use what I kind of defined up there to understand what this might mean. And literally, it would translate to 1, 0, 0 plus 3 times 0, 1, 0 minus 0, 0, 1. And the way you add and subtract these is you literally just go piece by piece. So if I go kind of along the top, it would be 1 plus 3 times 0, so nothing there. So just 1 plus nothing, then minus nothing. So we would get just 1 in the x component. And the y would be 0 plus 3 times 1 minus 0, which would just work out to be 3. And then the last part would just be 0 plus 3 times 0 minus 1, so just negative 1. So you can do that with vectors, with addition and subtraction. You just simply add and subtract piece by piece. What's a little weirder is multiplying, and that's kind of what I want to get into right now. But first, I want to explain a little more about a unit vector. So it's important that you know how to calculate these, and it's not bad actually at all. So if I take vector A and I literally just divide by its magnitude, which we just denote with those 2 bars like that, then it's going to be a unit vector. Basically, in this case, the red vector here is going to shrink down to the blue vector, and that blue vector would be length 1. So just to kind of work through this one, so vector A right now would be given by 3, 4, and its length would basically just come from the distance formula. You're just going to be doing this distance squared plus this distance squared, and then the square root of it. So the length of this vector, which really just comes out of distance formula, is going to be 3 squared plus 4 squared, and the square root of that, which is 9 plus 16. So the square root of 25, which is 5. I made this one nice. So if you just take the vector 3, 4, and we divide by 5, basically, then we would have 3/5, right? And we would have 4/5. And that vector, maybe I should have done it in blue, circle it in blue. That is the little blue vector right here. And you can kind of see that like it's moving 3/5 to the right and 4/5 up. The way I really just think about unit vectors is that you're basically you're taking something, and if you divide by exactly its size, it's sort of like dividing 5 by 5 or something like that, where that equals 1. And so if you do this with a vector, then it's just going to give you a vector of length 1. And you can check it. I'm not going to go through it right now, but if you find the magnitude of, I got to be better about this. So I'm actually going to use the hat notation. So a hat, okay? If I find the magnitude of a hat, I guarantee you it's going to be 1. It's going to be a vector there of length 1. So to do something like this, if I wanted to find a unit vector in the direction of this messy looking thing, first you should find the direction of it. To find the direction of something like this, you really just need to look at how much you move in each I, J, K direction. And so we can really just see that we move 2 in the I direction, which is X, -1 in the J, which is Y, and -2 in the K. So like a vector that would be parallel to this unit vector that I'm going to create would be something like 2, -1, -2. And then you could just find the magnitude of V, which I would just do as, taking each piece and squaring them and adding together. It's really just here a 3D distance formula, but it's going to be 2 squared plus negative 1 squared plus negative 2 squared. And if you work that out, that is 3. And so then a unit vector, I'm going to call it v hat, is going to be just, you can even do it like this. We could say 1/3 of v, or even 1/3 of 2, -1, -2. And that would be a unit vector in the same direction. So, last but not least, I want to talk about dot product, which is basically multiplication and vector multiplication. That's how I kind of want you to think about it in the beginning. Eventually, I'm going to show you a video that talks a little more about what's going on, and there's a little more to it, but basically, it's like vector multiplication. And it's pretty straightforward to do. So we define it as just taking each part of the vector, the corresponding parts, multiplying them, and then just adding it together. It doesn't give you a vector, which is important. It actually gives you what we call a scalar. And so if I was going to do it for u and v, it would literally just look like 2 times 5, because those are the corresponding x parts. And then I'd add it to -2 times -4. And then I would just add it to -1 times 0. And if you just add all that up, I think you should get 18. If I did my math right, yeah. And so that's it. That's how you multiply, in quotes, a vector, or 2 vectors. And for right now, I just want you to know how to do it. There's a few problems on the homework where you'll kind of have to use this, but there's a whole bunch more to say about it for right now. I thought since I showed you magnitude and dot product, it'd be kind of good to show you this. So I'm just going to prove that these two things are actually equal. And so I'm going to define vector A as just A1 and A2. And the notation for dot product, I should probably go back there for a second. It literally is a dot, just like you see there in the definition. So if you see a dot between two bold things, or things that have like, I'm going to do this in the corner. If I see V with an arrow, dot U, or something with an arrow, I know those are vectors because they have little arrows on top. And the dot really tells me I'm doing a dot product. It doesn't mean multiplication in the normal sense. We're doing something else here. So back here, if I was going to prove this, if I want to show an equality here, best way to just prove this is to take just compute, like in symbolic form, the magnitude of A squared. And then we'll look at A dot A, and hopefully those two things are equal. So just doing, again, distance formula. For the left side, we would have A1 squared, right, plus A2 squared, and the square root of that, right? And if I then had to square it, though, right, I would get A1 squared plus A2 squared. So that's kind of the left side. And A dot A, right, is, if I use this definition back here, we just need to multiply corresponding components. So A1 times A1 would be A1 squared. And then we add it to another corresponding components multiplied together. So we just have A2, whoops, looks like a 9. A2 times A2, which is A2 squared. And, oh look, A1 squared plus A2 squared is equal to A1 squared plus A2 squared. So, yay. And we could do this in higher dimensions, but this is actually going to become something that's very useful down the road. We will prove some things using this identity, but as you can see here, the magnitude of A squared is actually just equal to a dot product of a vector with itself. which is an important fact for later. The last thing I want to show you here is just kind of geometry related to the dot product. So I will actually be proving to you this relationship right here. And it's super, super important. I think anyone who's taken Calc 3 feels like they end up using it just all the time. And we will come back to it, but there is a geometric piece to what the dot product is doing. And you can see it because you can rearrange this identity right here into something that equals a cosine. And if you think about, I just think about unit circle. If I was over here in the first quadrant, right? I'm going to try to squeeze this in. I'm going to do it over here, but not in that color. So I use the acronym when I teach unit circle stuff to my Algebra 2 students. I teach them all students take calc as a way to remember what trig functions are positive where. And so in the first quadrant, right, the value of the cosine is positive because everything's just positive there. In the second quadrant, right, over here, then we have that sine is positive, and so that means the cosine's negative. And kind of smack dab between those two, if you think of 90 degrees, for this one, you can't really use the all students take calc. You just have to kind of know unit circle. But we should know that the cosine is going to be 0 there, right? And so the important takeaway here is that the dot product basically tells you something about the direction the vectors point, just like those pictures I kind of circled up there, and also this one that I didn't circle. But if you find that the angle what I want to say is that the sign of the dot product tells you something about the angle, not the angle telling you something about the dot product. Because a lot of times we'll just be taking a dot product, and if we notice that the dot product of two vectors is positive, then we know that those two vectors basically point in the same, I'm going to put that in quotes, kind of vague direction. Just like that picture I circled up there. And then if you know that they are negative, the dot product is negative, then the vectors basically point away from each other. Away. And again, I'm going to do that in quotes. So probably the most important one is the last one, because if you find the dot product between two vectors is 0, you know those vectors are perpendicular. And this again makes me think of things in physics, and I mean really I'm just going to keep going back to physics. But there's tons of force problems where you take the dot product and you find it's perpendicular, and you're like, oh, those forces are 90 degrees, perpendicular to each other. So that is just an important piece of the geometry of the dot product. So last but not least, I just want to show you kind of how we could use this. So if I wanted to find the angle between the diagonal of a cube and one of its edges, let me just start by drawing a picture. So I've got a cube here, and I want to find the angle between the diagonal of the cube and one of its edges. I personally would think of this problem as kind of snug right up against the origin in 3D space. So I'm going to think of this vector, and then I'm going to think of my diagonal one going from here, it's hard to do dotted lines on here, back to that corner. And so the purple vector down here is a little easier to kind of define. It would just be, if I can do this with any length, right? So I think the easiest one would be length 1. So I'm going to call that 0, 1, 0. It's really just j hat, right? And then the orange vector, I'm going to call it w for no good reason. I am moving, I'm still moving nothing in the, I am moving in the x. I'm moving back here, -1 in the x. And then I can think of moving 1 over in the y. And then I move 1 up in the z direction. So now if I wanted to find the angle between them, that's where this last formula would basically come in. I could use the formula there in the top right corner to do this. So if I just have the cosine of the angle between them, this is hard to draw here, but that's what I'm going to be solving for. It's just going to be v dot w and then over the magnitudes of those two vectors. And so this dot product would just be, again, 0 times -1, so 0 plus 1, then 0 times 1. So we're just going to get 1, which is nice, on top. And then the magnitude of v would just be basically 0 squared plus 1 squared plus 0 squared, square root of that, which is really just a 1. And the other one is going to be square root of 3. And so then, really the angle between them would just be the inverse cosine of 1 over root 3, which I worked out before is about 57 degrees, I think, if I did that correct on my calculator. But really, this is the best answer anyways, right here. So that's just an example of how you could use this kind of geometric understanding of the dot product to figure out the angle between the diagonal of a cube and one of its edges.